Hello, everyone.
Miss
Thank you.
Pointer.
Thank you for the introduction. Thank you, ladies and gentlemen, for attending. So I am Marwa BETTAIEB, and it's a pleasure to present to you our project about the effect of microstructure on the mechanical creep properties of 316LN austenitic stainless steels. Today, I'd like to cover three main points, starting by the studied steels, then their creep behaviors, and finally their creep damages and their microstructural evolution at the studied creep test. But first, let me introduce to you why we are interested in this project. So as part of the developments of the fourth generation nuclear reactors, specifically the sodium cooled fast reactor presented on the left here, the non-replaceable components are designed to operate in their hottest part at 500 degrees C up to 6 years. So the principal damage here is the long-term creep. The material used for these components is a 316LN stainless steel. Many manufacturing rows are used here, so the majority of our components are rolled, and the large-scale components are hot forged, adding a small amount of niobium to prevent grain growth during the manufacturing road at high temperature. And so that our main aim here is to understand the influence of the chemical composition and the manufacturing road of the studied steels on the creep behavior, mainly on the minimum creep rate and the creep damage mechanisms. Let's take a look on the properties of our stainless steel. So here we have two stainless steels, 316LN stainless steels that have approximately the same chemical composition. But like I just mentioned, the hot forged material, we added a small amount of niobium to the hot forged material to prevent the grain growth during the hot manufacturing growth. I'll just keep please in mind this color code for the rest of the presentation. So the niobium-free alloy is presented in green, and the niobium-rich material is always presented in red color. For the tensile mechanical properties, the niobium-free alloy has a slightly higher tensile resistance and a superior yield strength compared to the niobium-rich alloy at both room and high temperature. If we take a look now at the microstructures in the as-received state for the two alloys, we can note here a typical microstructure, equiaxed microstructure of 316LN alloy with 90 micrometer as average grain size against higher grain size for the niobium-rich alloy, which is twice the size of the other alloy. And here we can note also the presence of sub-grains. In this image of the niobium-rich alloy, we can note at the as-received state the presence of intergranular and transgranular nanoprecipitates that are also highlighted in TEM analysis. These nanoprecipitates are identified as niobium carbonitrides, and we can also see some dislocation lines observed at the as-received state of this niobium-rich material. moving on to the creep behaviors. So according to the CEA creep database, presented in this diagram by the minimum creep rate versus the applied stress at different temperatures, at the same, sorry, it doesn't work. At the same conditions, we can see that the minimum creep rate is always lower for the niobium-rich alloy compared to the niobium-free one. For the rest of the presentation, I'd be interested in the tests, the creep tests carried on 575 degrees C and 310 MPa. So if we look at these curves, we can say that the niobium-rich alloy, that 14% was measured for the niobium-rich alloy at the loading phase of the test, against only 8% for the niobium-free alloy. And during creep, we can note visibly that the minimum creep rate is lower for the niobium-rich alloy, with a longer creep lifetime and a lower creep ductility during creep. If we take a look at the creep damages, so here are two fractographies. On the left, the fractography of the niobium-free alloy, and on the right, fractography of the niobium-rich alloy. So visibly, we have different fracture types. If we look at zoomed in images, we can note through those dimples that the fracture is principally transgranular for the niobium-free alloy, and according to this image, where we can note the presence of straight edges and shiny surfaces, that the fracture is principally intergranular for the hot forged material. If we move on to observe longitudinal sections of the two alloys, so at the same area of from the damaged part of the two materials, the two specimens, we can see on the left that we have a higher number of cavities with greater cavity size for the niobium-rich free alloy, sorry. And we can note that the fracture is intergranular for the niobium-rich alloy, because the cavities follow the grain boundaries. But we can't conclude about the type of fracture of this alloy. So that's why I'm showing here NBSD map for the two alloys. So the map on the right just confirm what I've said for the hot forged material. And on the left, we can see that the cracks also are intergranular, but the propagation of our cracks is transgranular. Let's now take a look to the microstructural evolution of the tested specimens. We can note for the two alloys that the presence of intergranular precipitates, and the precipitates for the niobium-free alloy are identified through the literature as M23C6 probably. And we can note the presence also of transgranular precipitates for the niobium-rich alloy. And in both cases, we can here see that the cavities initiate from the intergranular precipitates, and that the crack is, and the crack initiation then is intergranular for both cases. If we compare now our results for the damaged part to the heads of the specimens, which are non-strained parts, but hot-aged ones. We can see here a few number of intergranular precipitate for the free niobium material, which is lower than which we have seen for the niobium, for the damaged part, sorry. And then we can say that the creep accelerate the precipitation here in this case. In the other case, for the hot niobium, for the niobium-rich alloy, we can't really notice any differences between the head and the damaged parts. So to conclude, we have two different alloys of 316 austenitic stainless steel that differs by their microstructures. During creep, the niobium-free material is more ductile than the niobium-rich alloy, which is not the case for the tensile loading phase. We have longer creep time and a minimum creep rate much more lower for the niobium-rich alloy. And we can note that the structure is intergranular for the two cases, with intergranular initiation and transgranular crack propagation for the niobium-free alloy, and intergranular propagation and initiation and propagation for the niobium-rich alloy. So the question here is, how can main microstructural elements influence differently both creep and tensile mechanical properties? And the work is always on progress. Before finishing, I'd like to thank my co-authors and everyone that cooperated for this work. And thank you all for your attention and your interest. And it's my pleasure to respond to your questions.